In today's class, we're going to talk about exceptions to the octet rule. Now, there are three major exceptions to the octet rule. Those are what we call odd electron complexes, right? Which are going to have an odd number, so we're going to have an unpaired electron somewhere in the structure. These are also sometimes called free radicals, and these are highly reactive compounds. Not a whole lot of them out there. For example, NO is one of them. And we'll draw the structure here of NO in a second so you can see what it looks like. There are compounds that have incomplete octets. These are going to be dominated by the elements in group 3, right? So boron and aluminum, they are perfectly happy having 6 electrons instead of 8. So this is where we have what we call incomplete octets. And then, as we saw before, in our last example with selenium, the SeO3 ion, that we can have expanded octets because of the empty d orbitals. We can have more than 8 electrons, and this is going to be for elements that are in period 3 and below, not period 2 elements. For example, carbon, nitrogen, oxygen, right? They will not expand their octet. Okay, so we're going to get into each of these, but let's just start by looking at NO. So if we do the valence electrons in NO, right, we're going to have 5 for the nitrogen, 6, so we're going to end up with 11 electrons. Okay, so if I draw my structure, so again, not a whole lot here. We got a diatomic, so we're going to connect them with a single bond. So that leaves me 9 electrons. Now, clearly, if I wanted to complete this with lone pairs, nitrogen needs 6, oxygen needs 6. That's going to take 12. I don't have 12. So I could do something like this, right? I could say, well, I'm just going to space them out, right? I'm going to give 4 here, and I'm going to put 4 here. That uses up 8, but I still have this extra electron. So what do I do with this? Well, okay. Now, it's not just as easy as plucking it on here and putting it on one of the atoms, so we have to think about this a little bit. So if I compare oxygen and nitrogen, oxygen is more electronegative. So one of our things that we like to think about is that the more electronegative atom is going to get more electrons. Right? So we typically want to keep more of the electrons with the more electronegative atom, or the oxygen. So we could just go ahead and put that on here, but we're not going to do that because that's going to lead us down the wrong pathway, I think. So let's look at the structure one more time. So even if I put that electron, so regardless of where I put it, it is not going to satisfy the octet of anything. So we would end up with, 5, we would end up with 7 on one and 5 on the other. So neither atom is going to have an octet. So we know that we're going to need a multiple bond. So we're going to need to make at least one extra bond. So the question is, where do we take the electrons from? But again, we take them from the lower electronegative because it's going to be the one realistically that would lose electrons. So let's do that. And now we have, let's do this in a better color. So now we have this structure, right, where we have the 1 lone pair over here. We still have the 2 lone pairs over here with our double bond. So now we've given oxygen an octet. So that's all good. But if we look at nitrogen, it only has 6. So we can't get it all the way to 8, but we can get it to 7. So we can end up with nitrogen having 7, oxygen having 8, right? So this is the best that we can do. Now, if we're curious to know, okay, well, is this one really better than this one? So let's say if I did the other way and I ended up like this. If nitrogen had the octet, but oxygen only had 7 electrons. So what's going to tell us? Formal charges, right? So let's do this one. We got 5 and 6. So the nitrogen has 3 non-bonding, right? So since we have the single one, it's sharing 4, so half of that is 2. We get a 0. So here we have 6. We have 4 non-bonding, sharing 4, half of that is 2, 0. Looks pretty good, right? So let's think about the nitrogen. What if we have this structure? So we have 5 and 6 to start with. Here we have 5 minus 4. Half of the 4 shared, that's 2. So 5 minus 6, negative 1. So with the oxygen, we have 6 minus 3, minus half of the shared, the 2, 6 minus 5, positive 1. So here again, we have formal charges, which we don't really want. And beyond that, the negative formal charges on nitrogen, the lower electronegative atom. So, for various reasons, this is not the structure we want. That is. And in general, if you see these kinds of things, the lone electron is going to end up on the lower electronegative atom, right? It's the one that's going to sacrifice having the paired up octet. Right? Okay. So now let's talk about the other two types, incomplete octets and expanded octets. So incomplete octets, again, this is going to occur in group 3. So I got some structures from boron here. And so for example, we have BF3, right? It's going to look something like this. We have BH3. It's going to look something like this. Now, these are both perfectly fine Lewis structures, right? Boron is perfectly happy only having 6 electrons around it, right? It's in group 3, only has 3 valence electrons, right? It's going to be good and happy. Now, we can do some formal charges if you want to. So we can do the boron, the 3 fluorines, right, which are going to be the same. So boron has 3 valence electrons. These have 7. The boron, right, has no non-bonding. It's sharing 6, so half of that is 3. So we get a nice formal charge of 0. The fluorines have 3 lone pairs, so that's 6 non-bonding. They're each making 1 bond. So half of that is 1 electron. So 7 minus 6, all of these are 0, right? So, perfectly happy. Let's say we tried to do this. We tried to make a double bond, just like we would maybe to satisfy the octet of boron. We'd end up with something like this, right? If you calculate the formal charges, right, the fluorine that you just moved would end up with a positive 1 formal charge, boron be negative, right? And this doesn't make any chemical sense, right? Fluorine being the most electronegative atom, right? There's no way you're going to have a positive formal charge on that. It should be negative if anything. And boron, again, for the same reasons, right? It's not going to take more of the electrons from fluorine. So this kind of structure makes no sense. So again, just a little way to show that, boron, and also you could have aluminum here, are perfectly happy only having 6 electrons. So group 3, you're going to see these incomplete octets. Now, one thing that's much more common, right, is expanded octets. So we start getting into compounds that have more than 4 things bonded to it. So we start getting into things that have 5 and 6. So hexavalent or 6 bonds is going to be the most that we're going to see. But in order to make those complexes, of course, you have to have more than 8 electrons around the central atom. You have to have, in this case, you have to have 10 or 12, right? So we have to expand. And again, this can occur as long as you're in period 3 and below. So while nitrogen can't do it and oxygen can't do it, sulfur can do it, acetine can do it, right? So phosphorus can do it, So we're going to see these kinds of compounds. And these are perfectly stable, and you could draw formal charges to show that. But for now, we're just going to go at that. We're going to approach these where we can expand the octet beyond this. Now, what if you look at a structure like this? So I'm going to give you the structure of sulfuric acid. Right? So this one is a bit of a unique structure. So if I look back at these, right, if I were to do the formal charges of the atoms here, all the fluorines would be -1. Or sorry, I did that wrong. All the fluorines would have a formal charge of 0, right? They'd have 7 minus 6 minus 1. So halogens, as we'll come to know, like to make one bond, right? They need one electron. Just like oxygen likes to bond twice, halogens like to bond once. Nitrogen likes to bond 3 times. The number of electrons they need to satisfy their octet is typically how many times they want to bond. So these are all going to have formal charges of 0. Sulfur is also going to have a formal charge of 0, right? Because it has 6. It has no lone pairs. It's making 6 bonds, so it's sharing 12. So half of 12 is 6. So 6 minus 6 is going to give us a 0 formal charge. So these are perfectly stable structures, all 0 formal charges. What if we do something like sulfuric acid? So if I were to draw the structure of sulfuric acid, my original structure, I might end up with something like this, where I have, so this is H2SO4. So I have my sulfur, I surround it with the oxygens. Now the hydrogens, of course, could I bond them to the sulfur? I could, but what you'd see is that's not going to be a great structure. But more likely, they're going to be bonded to the more electronegative atom, because remember, the electronegative atoms like to bond twice. Oxygen likes to bond twice. So it makes sense to put the oxygens on the sulfur, or excuse me, on the oxygen. And so you end up with a structure that looks like this. Now, unfortunately, if I do the formal charges here, I end up with, these being 0, of course. So the oxygens that are bonded twice and the hydrogens that are bonded once, they're all good. But the oxygens that only bond once, they have a -1 formal charge, and the sulfur ends up with a +2 formal charge. So ideally, we'd want to fix this. So formal charges can tell us, just like we saw in that SO32-, right? They can tell us, they can indicate when we have resonance. And we can expand the octet to accommodate that. So if we think about resonance, we go back a little bit, think about resonance, right? There's really 2 places where we see resonance. We see resonance where we have a double bond that we can move around, or maybe choosing between whether to use 2 double bonds or a triple bond, right? But it's really just a matter of, where we put the double bonds, or if we use 2 double bonds or a triple bond, right? That's kind of visually a little bit easier to see. There is another kind of resonance where we really don't see it until we do the formal charges. And we do the formal charges and we realize, oh, we have positive formal charges on the central atom and negative formal charges on the external atoms. Can we reduce these down so that they don't have any formal charge, which is the ideal? Well, if our central atom, again, can expand the octet, we can use multiple bonding to expand the octet and thus reduce the formal charges. So we can go from a structure like this to a structure like this, where everything has 0. Now, unlike selenium, right, sulfur is a +2. So we can do this twice, right? We can take a pair of electrons from here and make a double bond. That gets this one to 0. It would get this down to -1. We can do it again, or excuse me, +1. That'll take this one to 0 and get that one from +1 to 0. So since it's a +2, we can make 2 double bonds. And now we have a better structure with all 0 formal charges. And this is going to be the best resonance structure for sulfuric acid. Now, I will point your attention that I will have a video or an external video that goes through the Lewis structure of this. So if you want to get a little more insight in drawing the Lewis structure for this, I would suggest watching that. This is going to be a good thing because there's several structures that you might come across that we want to recognize and say, oh yeah, the formal charges tell me that I have resonance. So that's one of the useful things that we can do with formal charge. It can tell us which resonance structure is better if we have already seen the resonance structures, or it can also indicate that I need resonance structures or that there are better resonance structures out there. All right, so we're going to conclude this video here. In the upcoming ones, we're going to talk about bond energies a little bit, and another use for bond energies, and then yet another way that we can calculate the enthalpy or heat of reaction.